Good morning. This is Mr. Weiss for 9E&F Physics. It's the live stream, and if you miss this, we'll be talking about half-life, critical mass, and if we get that far, how to make an atomic bomb. We'll see. So I'll just wait for folks to come on here in the next few minutes. We'll take a little roll, and then we'll get rolling as well. Let me bring my desk over here, also known as a box. And I'll put up behind me a whiteboard so we're all ready. I got a couple already, so say hello so I know who you are. Leia's here. I'm well, thanks, Leia. I hope you're well too. I hope we can actually see each other someday, all of us. That would be very nice. So I got Leia. I got 4 others. Super. Tell me who you are. Let's see that a little bit better. Yeah, that'll be okay. Got my, there we go. Got my markers ready, got my eraser ready, and I got, is this for my class? No, Freedy is not for your class, and I just wrote you guys a message, Freedy. I'm so sorry. I had to spend more time at school than I thought, so I didn't get back in time. I got back like 5 minutes before your live stream ended, so my apologies. The good thing is, Freedy, and pass this along all of 9D, is you guys are through all the curriculum for 9th grade. It's all done. So even if we don't meet again, you guys are set. And I cannot meet next week because I have teaching every day next week. So sorry, Freddie. Okay, 9E&F. Let's see who else is here. Tony's here. Micah's here. Tom is here. Oh, Ali is here and Noah Delps is here. Make sure I didn't miss anybody. So far, so good. A couple more on as well. So hello, Dominic. Hello, Natalie. Hello, Lucy. Whoa, a bunch are coming on. And Benedict. Hello, and hello, Alyssa as well. Very good. Hello, Santiago and Ben. The names are just stacking up. I love it. Hello, Larissa and Felina. Felina, I see I have your, I guess it's your sister for AP Chem next year, and that's cool. Don't know her, because I'll know her very soon. Let's see if there's anybody else that I haven't gotten. So far, so good. There's Deacon and there's Sarah. Welcome to both of you. Thanks for joining us, everybody. We'll get started in just a couple minutes. Hello, Emily. Hello, Jason. Glad you made it, Jason. Some of you have gotten so tall, and I see you now, and I hardly recognize you, and it's only been like 2-3 months. It's crazy. What will it be after the summer? You guys will all be 2 meters high. I won't be able to even crane my neck up to see you. Okay, I'll wait another minute before we start just to see if anybody else is coming. I'll count, but I got like 17, 18 so far. It's good. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18. And looking good. So maybe we'll go ahead and start now. Okay. So the last part of the curriculum you guys need are 2 things, and it's half-life. And we started with half-life last time, and we'll do a problem right now. And then it's nuclear fission. Hello, Muriel. So let's do our half-life problem that I think we started last time and did not do. Hello, Kira. And our half-life problem goes like this, okay? Recall a half-life, it's just the time for something that is radioactive to give off radioactive particles. Once half the particles have been given off, that's called the half-life. Takes a certain amount of time. Okay, here we go. Right. So this is going to be a half-life problem. And I hope you guys watched the last live stream if you weren't there. And it goes like this. We've got a human bone was found. Found with zero 0.0250 grams of carbon-14. Now, carbon-14, if you can see it in the, there you can still see that, that's the radioactive one, okay? So human bone was found with 0.025 grams of carbon-14. Originally, it had 0.12 grams. And Shilpa's here as well, but can't comment. Okay, thank you, Shilpa. Well, thank both of you. There she is, okay. Ship can't connect, but she is here. Got it. Yeah, thank you. And Melena's here. Good. Quick check there. Okay, recall that for carbon-14, I think we did it. It's good for stuff that hasn't been dead too long, so to speak. We can't use it for stuff that's millions or billions of years old, but we can use it for stuff that's thousands of years old. The half-life for carbon-14, I'll say given half-life of carbon-14, I can also write it this way, carbon-14 is, we're not going to give you the exact number. It's close to 6,000 years, so we're going to use that, okay? Okay, and that's all we got, and that's all we need, to be really honest. Okay, you'll learn in 10th grade about a math formula to do this using what's called exponential decay. But for now in 9th grade, we just use a table, and I think you'll find it understandable. I hope so. Okay, here we go. So make this table with me. I'll try and fit it on here, and I may have to flip back and forth with the shiny part so you can see it. Stay, don't fall over. So this is going to be number of half-lives amount C14 and time passed. So it's going to be 3 columns. If you can make that on your paper, that would be good. All right. Julian, oh, I got a couple others here. Whoa. All right, let me catch up. Maurice is here. Good morning, Maurice. As is Malin. And Julian L is here. Very good. Thanks for joining us, all of you. Okay, you ready? Now we can actually do this thing. So, kind of starts like this. We're going to begin with what we originally had. So the amount of, I should write here, this is in grams, amount of grams. The amount of grams that we started with was 0.12 grams. 0.12 grams. And the amount of half-lives that has passed by is none, 0. The amount of time passed is also 0 years. It's in years. 0 years, okay? Now, here's how this really works, because Priya's here. Thank you, both of you. Thank you, Priya, for joining us as well. There she is. Got it. Good. Okay, here's how this works. When you and I breathe, okay, we breathe in and out and we exchange CO2 with the atmosphere. A certain amount of Cs are C14s that are naturally radioactive. Not a lot, not enough to hurt us, but just enough as we breathe air, okay? As soon as you die, sorry about that, as soon as you die, you stop exchanging air with the environment. And therefore, the Cs that are in your body, the carbons, the ones that are radioactive, start to break down. That's why everything has a known amount of carbon per kilogram or whatever. And I can actually calculate what that is based on the mass of an object. So that's not just pulled out of my hat, okay? Right, okay, so here we go. So 0.12 grams is the amount of starting stuff, like when the creature first dies, well, the person, because it's a human bone. And then after one half-life goes by, well, how many years then have passed? One half-life. Let's see if somebody can punch in real quick. So who's following? How many years have passed after one half-life? One half-life's over. How many years have passed? Let's see some more guesses. Punch them in. One half-life has passed. How much time has gone by? Read through the problem again. Yeah, exactly. So, I don't know what the real number is, Tom. I'm just going to say it's 6,000 years. So one half-life means 6,000 years have passed. And of the 0.12 grams, half of it has become something else. So we've got only half of that left. Ready? So I got 0. Well, half of 12 is 6, so 0.06 grams. Okay. The half-life is known, so I'm not sure, Leah, you'll have to be a little more exact, but half-life is known for carbon. It's 6,000 years. One half-life passes, that means 6,000 years has gone by. Of the original sample, half of the radioactive stuff is left. Let's keep going, and I think you'll all get it. Okay, here we go. Let's say another half-life goes by, so now 2 half-lives have gone by. Okay, 2 half-lives have gone by. How many years have gone by now? 2 half-lives. How many years is that over here? And if you want, you can crank out and figure out how much of this is left too. Okay? So 2 half-lives. And Tony's got it. Let's see some others come up with it. Sometimes it takes a little time for it to get over the internet to me. But it is indeed. It's 2 half-lives is double that, right? So 12,000 years have gone by. Good. How much of the radioactive stuff in the sample is still left? There's less left. So a half-life has gone by. So instead of Noah's here. Thank you, Noah. Good. Oh, you guys are quick. All right. And Marila's here. Hey, this is great. Lots of good participation. Appreciate it. You got it. Tom and others have it. So it's 0.03 grams are left. Okay, we could do this all day, but let's now look at what I gave you. All right, look at the top. The human bone was found with 0.025 grams. Hey, that's pretty close to this, isn't it? Pretty darn close. Good. So now we can do one more and say after 3 half-lives, well, how much time has gone by and what's left in our sample? Okay, 24,000. No, too much. 3 half-lives, not 4. So be careful with this one. 3 half-lives have gone by. How much time is that? Thank you, Natalie. 6 plus 6 plus 6 is 18,000. She's got it. 18,000 years have gone by. That's 3 half-lives. Okay? Good. Let's do this stuff then. It's 0.0015 grams. Is that right? Yeah, that's right. So therefore, let's compare with this up in our problem. Well, our sample is somewhere between 12,000 and 18,000 years old. So we're probably talking closer to 12, isn't it? Because 0.025 is much closer to that than this. So we're probably talking, so our bone, well, the bone that we found, is a bit over 12,000 years old. That's how you do these. You make a chart. Maybe I should have made it a little different and a smaller amount, but do you get the idea? That's kind of how this works. I may send you one last assignment to try, and it's to do some of these half-life problems like this, okay, with a little pretty easy math that I think you'll all be able to do. Questions on that before I change overheads? I'm going to get out overhead number 2. And what does this tell you? Okay, let's say that if it was a Stone Age person, it was maybe over 20,000 years old. The question might be for the guy who finds this bone, hey, is it a Stone Age ancient human? And the answer would be, well, no. If it was a bit over 12,000 and Stone Age began with 20,000 years ago and older, then it would not be Stone Age. So it does help figure out where something fits in various timescales and various scientific disciplines, like anthropology, archaeology in this case. Yeah, but lots of other stuff too. Trees can be dated here, right? I'm not talking about dating, kissing the tree, just figuring out how old it is, okay? So if it's a dead tree, you can not just count the rings, but if it's been dead in a long time, you can do this radiocarbon dating. The other thing that they can do this with is ice. So they've done this with really deep old ice under Greenland and Antarctica. If they bore down with a machine and they use the CO2 that's stuck in the ice, those little bubbles of CO2, and they can see how old that ice is and learn about ancient climate on Earth. That's how they get some of the information about the climate of today, is by using carbon-14 to figure out how old certain amounts of ice are and what the climate was like then. Cool, huh? So it's a practical tool. I see a question. Number of years per half-life. Yes, it is. Santiago, for carbon, it's, I forget. Tom will know the number. It's 5,700, blah, blah, blah. I just rounded to 6,000 for you guys. And for uranium, I think it's 239 or something like that. It's like over 1 million years is the half-life. So it's used for older stones and stuff. So very different things. This one is used for material that has carbon in it, something organic. So if you had an old piece of limestone, well, you could use it for that. Here's another neat thing about carbon-14. It's useful, but I can only go back so far. After I go back, here, I'm going to change boards now. Carbon-14 can be used for stuff that's back to about 200,000 years old. That's it. After that, it's so old, there's very little of it left, not enough to accurately date how old the object is. So can be used. So C14 technique can be used for, well, C-containing objects, carbon-containing objects, up to 200,000 years old. Yeah? Okay. And again, this is only one technique. There's other ones, strontium neodymium, there's rubidium, strontium, and potassium argon. At any rate, there's several techniques that are used by scientists, especially geologists. That's what I studied long ago. We use a lot of techniques to figure out how old stuff is. Let's go on. The other thing we want to start talking about today, and we'll see how far we get, is fission and how to do it and how to use it. Okay. There's how you spell fission. Can you read that? Kind of. I'll get the little shine away from it. So what is fission? I'm going to guess Tom or somebody might have it from another class. Fission. Anybody know what the heck it is? Wow, I guessed that right, Tom. Thank you. Yeah, when a nucleus splits into two or more pieces. And I'm going to add to this, Tom, when shot by a, and we'll figure out what we shoot it with. Now, if any of you have ever played pool, right, or billiards, you're going to understand what we're talking about. Here's my nucleus, all right? And again, forget the electrons for now. Here's the nucleus, full of protons and neutrons. We're going to shoot something at it, okay? Think of like shooting with a rifle or throwing something at it. If I throw an electron at it, it's too small. Electrons are puny. They don't do anything. I could shoot a proton at it. Why don't they shoot a proton at the nucleus? What would be the difficulty? Why can't they shoot a proton at a nucleus? What's the problem? No, they don't shoot it with a laser. They shoot it with a particle. Yeah, good, Tom. They repel because a proton is positive and the nucleus has positives and then a few neutral neutrons, and they don't do anything for the charge. So protons don't work. So therefore, can you guess from what Tom said, what do they shoot at the nucleus? What do they shoot? Exactly, Tony. So what do they shoot that could be used like a cue ball to shoot and fire and hit the nucleus? So there's a nucleus. And we're going to shoot an alpha particle is a bit too big because alpha particles have two neutrons and two protons. They're kind of big and they're also positively charged. So alpha particle won't work. We need something small and without a charge. They can't use an electron layer because they're too small. They weigh 1/2000th of a proton. They're just too puny. It would be like shooting a rubber band at a Cadillac. It's not going to do anything. Ah, thank you, Kira. Okay, so they shoot a neutron. So here's the thing, because they're neutral. So I'm going to shoot a neutron at this thing. Wham. That's like my bullet, okay? And then we shoot this thing and it breaks up into pieces. They're not 100% equal, but they're roughly equalish, okay? So I'll change colors and just kind of do some things here. Wang, 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 wang. Okay? Yeah, fission is just exactly that. Let's read again what Tom helped me get up above. When a nucleus splits into pieces, and then we're going to add when shot by a neutron. Okay, so that's breaking up one nucleus. But that's not much, gang, because they're really small. Okay, atoms are small, nuclei are even smaller. And what happens is, let's add one more little phrase here. When I do this, when a nucleus splits into pieces when shot by a neutron, I'm going to add here energy is released, and that is important. Turns out a lot of energy is released. Okay, a lot of energy released. But I got to have a lot more than one puny nucleus, okay? Okay, so here's what else. When I shoot this thing into pieces, quite often something else that comes off is one or more neutrons. So I'll put a couple of circles here. And why is that good? What could those neutrons go on and do now? So think of the process. Think I got a big hunk of uranium or whatever it is with lots and lots of atoms. What potentially could these neutrons go on and do? So here's some good guesses. I got a bunch of you today, so I'm expecting some good guesses. What could those neutrons do? So I shoot, and maybe a couple big pieces come off, and then maybe a neutron or two comes off as well. And those neutrons could, yeah, thank you, Ben. Good. So they could indeed split another atom, another nucleus, causing a chain reaction, or Tony, repeat the process. Exactly. They could repeat the same process. So let's draw that in our cartoon. I'm not going to draw it forever, but let's say by luck, this one, it's another nucleus over here, and breaks that up into pieces. Point up. I know we won't draw this all day, but I'll draw two of them. And let's say that shoots off another proton as well, another neutron as well. Okay? Good. And something else Ben said that's good is it can cause a chain reaction, right? I can split more atoms, I can split more nuclei. You catch up, I'm going to race the other board, and we're going to take that idea and see a little more about it and how that works. Where we're going to is nuclear bombs and nuclear power plants. Okay? Two things we need to know about. We good there? Hope so. Okay, so hope you got your cartoon done. Here we go. Back to board number one. All right, so the name of this idea to get this chain reaction going is critical mass. And it's kind of what several of you are alluding to, right? It's the fact that I can split enough nuclei so that it keeps the process going. So enough, let's say enough fission happens. Do I want to say that? I'll make it longer. Enough neutrons split enough nuclei, that's the plural of nucleus, okay, to keep the process going. The first place on Earth that they got critical mass was at University of Chicago. And I want to say it was like in the 1930s. Cosima is here. Thank you for telling me. Thank you and welcome, Cosima. Okay, so talking 1930s, this happened. First time on Earth at University of Chicago. What happened until then is, let's say that's my nucleus. They would split this sucker, bring, and then the process would stop. So scientists had to figure out a way to reach critical mass, to reach this stage when enough neutrons are splitting enough nuclei to keep the thing going. Well, there are two ways to achieve critical mass. And that's how we're going to say it. How to achieve critical mass. And you might say, okay. Oh, okay. And I have Lucy as well. So I have Lucy and Lucy. Good. 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 Okay. So, Mr. Weiss, what are you asking about? How to achieve critical mass? Here's what I mean. What can I do you suppose, to make it so that it's more likely that the neutrons that are released when I split one atom, what do you think I can do to make it more likely that the neutrons will hit other nuclei? I can change one of two things. What could I do? Okay, Santiago says they could shoot more neutrons at the nucleus. Yes, Santiago, they generally don't do that, but you could. But then you could also run out of nuclei. Interestingly, they don't do that, Santiago, but they could. And I'm not sure why they don't. Okay, Tom has one answer. What you can do is, instead of remember, most atoms are empty space. So they make it denser. They squish the atoms together so the nuclei are closer together. So one way is to increase the density. Looks like Natalie had the same idea. So increase the density of the atoms we want to break apart. We're going to call it the fuel. Okay, the atoms we're trying to bust up. Good. And there's a second way. And it's not really to speed up the neutrons. And heating them up doesn't really help either. There's something else simple you could do. I want to make it more likely that the neutrons hit other nuclei. More likely that they'll hit other nuclei. So we can make denser the fuel that we have, or what else could we do? Let's see if somebody said it already. No. So adding heat, any of that, adding speed won't work. Hey, good. Yeah, good. Santiago's got it. Tony's got it. Add more fuel. Okay. In other words, instead of having this much, now we got this much. And so it's less likely the neutrons can escape and leave the room. Okay. If I have more fuel, it's more likely they're going to hit another nucleus. So add more fuel. Good. We're ready to start making a nuclear bomb. And by the way, when I was young, we used the words critical mass to say something like this. Oh, the party was okay, but it never really seemed to have enough people. You know, we never really reached that critical mass. People really say it that way. So you can use critical mass as an English type phrase as well. Cool, huh? Physics, it's everywhere. Okay, right. Let's review the word that Ben said earlier, and it kind of goes like this. A chain reaction is when one step causes the next step, and on and on and on. It's not only used for fission, by the way. This phrase, chain reaction, it's used for a lot of stuff. But you know what? It's a good way to think of it here as a start of learning how to say or when to use chain reaction. Certainly, if I split one and those neutrons split another and another, that's definitely a chain reaction. So it was used then correctly here. Good. Let's talk about designing bombs. Please don't do this at home. If you do one at home, I'll become the first former chemistry and physics teacher that you've ever had. Let's erase. Sorry, I meant to do that on the floor. Oh, I hope it doesn't fall over. Okay. Bombs were first made in World War II. And the name of the project that made the bombs was called the Manhattan Project. The Manhattan Project. So we're talking like, I want to say 1943, really is when they started. Well into the war. It was not done in Manhattan in New York City, okay? It was done at a really remote spot. For grins, does anybody know where did they do the Manhattan Project? Anybody out there who knows for fun? Where did the Manhattan Project take place? Death Valley? No, but you're getting warm. Just kidding, Ollie. Certainly a lot closer than somewhere in Europe. Not in Manhattan, no. Okay. Though Death Valley is a good guess. It is out in the western U.S. Anybody else got a guess? Sometimes people know this for fun. Jason knows. Thank you, Jason. It was in White Sands, New Mexico. New Mexico. So in the Southwest. They wanted someplace that was really desolate, really deserted, and the place that the nearest town was called, Los Alamos. Exactly, Ben. Right. Very good. Yeah, they did in the 50s more tests there, Ollie. Yes, it's true. Okay, so here's what they did. They took scientists from all over the world that were part of the Allied powers, okay? And British guys, American guys, French guys, they took all these guys, and at the time it was all men. They stuffed them out in the desert and they said, guys, build us a bomb. And they wanted no distractions for these scientists. They just said, keep to yourselves and build us a bomb. The Making of the Atomic Bomb is a very interesting movie. If you ever want to see an old movie with Paul Newman, if you're bored, go see it. Probably might be even free on the internet. I don't know. What they did is they broke the scientists into two teams. We're going to call them the A team and the B team. Canada may have been involved. I don't know if they had scientists on the Manhattan Project, Emily, or not. They very well could have. It was lots of people, dozens of scientists. Okay, so the A team and the B team. And the A team used one fuel called uranium. And that's not going to work with it. And the B team used another fuel called plutonium. Each team had problems, and each team ended up being successful. We're going to see how. The problem with uranium was that it was really difficult to get. So what the uranium folks did is they had a laboratory at Oak Ridge, Tennessee. It was separated by mass, with little things called centrifuges. And they would separate it so they got the isotope that was radioactive concentrated. The radioactive isotope was called 235. So uranium-235. So they got enough of that, and I'm going to jump right down to the design because I see we're running out of time. Maybe we'll get some plutonium next time. So here's our bomb. It was called the Thin Man. And what they did is at the edges here, they had the uranium here and here. Uranium. I know you can't see that very well. There it is. So U for uranium. And on the end, the outer bits, they had this stuff called TNT, high explosive. And they had the whole thing in a really big cannon barrel. So imagine this is all inside of a cannon. I'll do it like a side view, okay? All right, so all this was packed into a cannon barrel. Uranium was probably expensive, although it was only used for the military then, Jason. So I honestly don't know if there was even a price on it at that point because it was so experimental. Okay, there maybe you can see the picture a little more. So again, we're running out of time, so I'm going to just tell you this one. They exploded the TNT, and what happened is the uranium on the sides went together. So when I explode it, let's see if I can do maybe black as the color here. So I explode it, and then the TNT drives the uranium to the center, and this one to the center. And when they reach the center, what have you done? You've increased the mass of fuel and the density because they're jammed together. And you reach blah, 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 blah. So first, we say it imploded. So imploded with help from the TNT. Then it reached critical mass. And exploded. Exploded. And it was a very well, this is one they tested first down in White Sands, but then they took one very similar to this and unfortunately dropped it on Japan and killed thousands and thousands and thousands of people. And the city in Japan, I believe this one was dropped on Nagasaki. And if we have time, we'll talk about effects on the human body of radiation. But it was really grisly. It was very, very awful. You can argue whether it ended the war early or not. I don't know. I don't know if anyone will ever know. But let's see how we're doing on time. We can at least start with talking about the B team now. The B team had another problem, which I won't write down, and it's this. Plutonium is very, very toxic, and it reaches critical mass too easy. So when they tried to take bits of plutonium together, it would explode literally in the lab before they could ever make a bomb out of it. So use plutonium, but Pu is the symbol. Plutonium reached critical mass too easily. So they could not use the same design as the A team. And by the way, I'm simplifying this a bit, as you could imagine. Okay, that's the basic structure of the Thin Man bomb, but there's more details that I didn't put in. Okay. All right, so what did they do to reach critical mass? Am I going to be able to do it in 1 minute? No, I'm probably not. So I think whenever I see you, whether it's in school or whether it's on another live stream, we'll talk about how the B team, the plutonium team, made a bomb that also did actually work. And that bomb was dropped on Hiroshima, another Japanese city, during the World War II. Okay? So that's kind of the deal with bombs. Once we finish bombs, we're going to do nuclear power plants and at least talk about how this process of fission can be used at least for something good, and that is to make electricity. Leah, I asked to have 9F. I actually asked to have 9F at school, and they said there's probably not going to be time. So I'm guessing I won't have 9F at all until maybe I get you next year if I'm lucky. So, is a nuclear bomb heavier than a regular bomb of the same size? No, I don't think it is, Jason. Not necessarily. Not necessarily heavier, just a lot more explosive, because the TNT has a certain amount of power, but the uranium, the power that for a single gram of uranium is so much more than TNT. So for a smaller weight, Jason, it has a lot more explosibility. Is that a word? I don't know. Thanks for your comments, questions, and all your participation. We'll see you again soon, and stay healthy.